I think we can start the session. Good evening, everyone. My name is Aveen Dayal. I'm a PhD scholar at IIT Hyderabad, and I will be conducting the live sessions for the course Deep Learning for Computer Vision, taught by Professor Vineet. And this is the week 9 for the live session. So I will just start sharing my screen, and we can start with the today's session. So, like always in every session, so basically the goal for these sessions are to have some sample example problems related to the content taught by the professor in the previous week. So, in the last week, Sir taught about attention and transformers. So, I'll explain a bit more about these concepts, and after that, we can see some example problems where it is used, like image captioning, tasks, and everything. And after that, we will go for the code walkthroughs, and we'll be covering two code walkthroughs today related to the last week's RNN and also a little bit related to the Siamese network, which was your assignment problem. So, yeah, start. If you have any questions or anything, you can unmute and ask. Since the class strength is less, I think that would be fine. I hope I'm audible. Maybe if someone can confirm in the chat. Yeah, okay. Thank you. So coming to the RNN tasks, which we talked about in the last week. So in last week, we talked about different tasks like translation. The neural machine translation is the model, and the task over here is the language translation. So which means that basically, if you have your input in one language like English, and you want the output to be in another language like Hindi, how do we make a machine do this translation automatically? That is what this particular field is called as neural machine translation. And apart from that, we also saw another example called image captioning, where the goal was if you're given an input image, RGB image, like you can see in this particular picture, uh, there's a woman and a child, and they're playing frisbee. And if you give this input image to your model, initially it is given to a CNN, which is then later sent to a RNN, and then we decode what particularly the activity that is happening in this particular image. So in this particular case, like your decoder will basically tell you that a woman is playing in the park or something, a similar caption like that. So this is another task called as image caption. Apart from that, we also saw tasks related to videos on how each video you can classify them, or you can basically frame by frame video classification can also be done. And we saw other examples for RNN. But the problem with the current RNN tasks, like for example, the problems with the current GRU or LSTM, is that the information bottleneck is present. What I mean by that is, so for example, if the input sequence is a very big, is of a big length, like for example, if you see in this example, the first paragraph, after meeting a comrade at the last position, it's a very big paragraph, right? So such a big input, the LSTMs and GRUs are not able to model inputs which have longer sequences. This is because although they have the gates like forget gate, input gate, and output gate, they have a particular limit up till which they can actually pass on the information or carry on the information seen at a particular time step in the past to a particular time step in the future. So there is a limit up to which this particular information travel can happen. So because of these, people have identified that several tasks, like the translation task itself or summarization task. Summarization task means when you're given a big paragraph like this, and if you want to summarize it in one line, or if you want to ask some questions, so those are all different question and answering tasks and everything. All of them require a RNN model to read a lot of big sentences and big paragraphs and everything. So in such cases, the existing RNN models based on LSTMs and GRUs were failing. So to overcome that, people then started using something called as attention. So attention can be applied in two different types of data. We have attention for temporal data and we have attention for spatial data. So first I'll explain attention for temporal data a little bit and then I'll move on to the spatial data. So in your particular case, it depends upon your task also which you're doing. If it's a task like image captioning, your data will be spatial and temporal. If it's just a task like translation and everything, it will be completely temporal. So based on the task, you can use attention whenever necessary in that context. So attention, so well, we are familiar with nowadays ChatGPT, transformers, and everything. So ChatGPT transformers, they all contain something called as multi-head attention, which we'll talk later. But the concept of attention itself is a old concept where people started using, I guess, back in 2015 or 16 in models called as BERT models. So BERT models were very famous. They were large language models, and people started using attention type of operation or a concept in those models. And later, over a period of time, people then started realizing that we don't need RNNs at all. We can just use attention only completely. And that is where you see nowadays your ChatGPT or other models where they just use only attention, which we call as transformers. So, but attention itself is an old concept. That is what we have to remember. So what attention uh, conceptually does is, so imagine if you're looking at a image, sorry, imagine if you're looking at a paragraph like this in the second English to German translation. So if you're translating the word to reach into German, which is this particular word uh, colored in red, so we need to focus out of this entire input sequence only on these two words. And we don't need other words or we don't need to pay a lot of attention to other words in that sentence when we're translating to reach to German. So this particular type of focus on certain input sequences is what attention wants to do. So attention wants to basically try to make the model learn to focus on what particular words given your previous output. So in such way, you can just conceptually visualize, understand what attention is trying to do. So how does it do? So in previous models where people used with RNN combined with attention, they use this concept called as a weighted vectors on all the previous hidden time steps. So as you can see, if we consider this particular context vector CT at this time step T, this context vector CT is nothing but a weighted addition of all the previous hidden states up and like from 1 to the entire time sequence like length, which is capital T. So this context vector T is basically, you can say that as the word suggests, context, right? It is trying to basically see out of all the input sequences, this particular output will depend mostly on what particular hidden states of the input. So that's why we have these weights. So based on these weights value, we can basically then say okay, particular H2 or particular Hj has more weight, which has more alpha value, and then it means that okay, for this particular CT the focus is more on H2 and Hj, and this is what attention was trying to do. And how do we calculate these weights? Alpha T to alpha capital T is basically used in this formula. Exp is your exponential function. Exponential, you get your score. Your score could be, I'll explain what all score functions you can use. So in simple terms, score could be any similarity function like cosine similarity or L2 similarity or any other similarity function can be used. So you get a scoring function, similarity function, and you send that value of scoring into the exponential of that particular times previous time step t minus 1 of the sequence, output sequence, and then divided by all the other particular sequences, which is traveling from uh, 1 to the capital T. So the division is basically used for normalization of this particular alpha term. The major concept to take away is you're using some similarity function and you're sending it to exponential to make it a positive. So that is what this particular alpha is doing, and you will over a period of time during training period you will learn okay what particular at what particular context CT what should be the alpha values for all the hidden states. So this is how people used attention and temporal. I hope this is clear. If you have any doubts, you can always message in the chat or you can unmute and ask. Just pause for a quick minute. And if you have any doubts, you can ask me for this particular attention mechanism. So moving on, now yeah. Do you have a question, Jitendra? Your voice is not audible. Can you just unmute and ask again? Okay. If you have any question, please. Okay. In a way, yes, you can think of it like ADA boost concept. Yeah, the boosting concept. But here you have to see in boosting, every sample is different. Like here we're talking about just one sample. So x1 to xt is not different samples. This is just one sample. So that difference is there, but concept is very similar to boosting. You can think about it that. So after attention and temporal data, we move on to attention for spatial data. Like we saw examples, sometimes even the spatial data needs to be in some sequence, which is temporal sequence, and we need some sequence models to model this particular data. So we need attention also at that particular for such particular data. So first, if you look at the topmost block left side, which is written as encoder. So what we do in this usually is you have your typical CNN. You take your input image, which is your RGB or grayscale, whatever image. You take that image, you send it to your CNN, which is your standard ResNet or any CNN backbone, and then from the last layer of the CNN, you usually send it to a fully connected network, and then you send it to your final classification layer to say what particular class it is or object detection. You do that. So this is a typical CNN network, what is written as encoded. Now, if you want to see if once we convert after the last layer of convolution into this fully connected, we lose the spatial information. What I mean by losing spatial information is if you look at the last layer, which is shown in the bottom part, M cross N cross C, this particular this particular feature map can always project back into your original image. You just have to do some manipulations because, like, if, for example, if you do 3 times convolution, then you'll have to do 3 times deconvolution, and then you can project back this particular element in M cross N cross C will actually be nothing but containing this in the entire image, this particular part of the input image. So this particular input image is getting encoded into this particular block in M cross N cross C. So as you can see, spatial information is still being preserved. It's just that we are condensing the information like through all the CNN layers. We are reducing the dimensions of these spatial maps. But at the end of the day, spatially related objects are still the same. So in simple terms, what I mean is, if in the input image, in this yellow color block, if I have a bat and a ball present in this yellow color space, so after your convolutions, 3 convolutions, the final layer, which is this block which you're getting, in this particular yellow color block which you see, right, that will still have the bat and the ball information encoded such that if bat and ball are like 3 units away in this the original image, it will still be some 3 units away only. But what that unit, the ratio will be the same, but exact unit values will change because we are condensing the information. So that's what we mean by spatial information is being retained. Objects located at different locations in that image will always remain the same when even when we are doing convolution. That is actually one of the reasons why CNNs also work. So now, if we use this last block of the CNN, and if you use this M cross N cross C, and if you see on the right side, you unroll this M cross N cross C into C vectors. Each vector is of the dimension 1 cross 1 cross C. So you'll have M cross N vectors, and each vector will have the dimension 1 cross 1 cross C. So this total vertically, if you see, there will be m into n vectors. So, and all these vectors, then you can apply a similar attention mechanism like this formula over here. Ct is equals to alpha tj head j, where j is from 1 to capital T. The same formula, you can assume these h1 to h capital T as nothing but these vectors starting from this top one going to the end, and total there'll be mn vectors, m into n vectors. So you can now understand this hidden states to be vectors, and you can apply this whole concept over here. So in this way, you're now making sure that you're paying attention to the in the image. You're now looking at, because like I said, this particular yellow block corresponds to a certain part in the image. Now with this attention, we are trying to figure out which part in the image is actually contributing to that particular output instance. So in a way, we are basically focusing on a particular pixel intensity values when we are training the model. So that is what this particular attention spatial data mean. So I hope this is clear. Maybe again, like I'll quickly pause. If you have any questions, you can unmute and ask, or you can also put it in the chat. So moving ahead. So once we have attention spatial data, so now I'll just talk about a little bit about the scoring functions. So like I said, the attention mechanism itself, they depend on this term called as alpha, because we have to give weights to the hidden states, right? And this alpha in turn depends upon the scoring function, which is basically a similarity function. So as you already know, there are several similarity functions available. It's not just cosine similarity, or there's so many others available in the world. So these are some of them, and these are again not the exhaustive set. There are, you can always find more better attention alignment scores, or you can also always create your own attention alignment based on a similarity function which you create. So to just summarize, we actually use this particular in the nowadays world in transformers and chat GPT and everything. Most of them actually use the last one, which is your scaled dot product attention. So it is an extension of the previous one, which is your dot product attention. So dot product is nothing but, like, we just find the dot product between two vectors. In a way, we find the similarity, right? Like an angle between them. So dot product also gives a similarity between two vectors. The similar the two vectors are, the higher the dot product will be. So in that way, we find out the dot product score. And since we normalize it because of computational issues when we are training, if you don't normalize, then the score becomes very high and it will be hard to train. So once we normalize it, we get the scale dot product attention. So this is the final one which people use in transforms nowadays. Apart from that, you will have some general attention mechanism where this WA itself, depending on what the WA value will be, you'll get different attention. So if WA is 1, you'll get your dot product attention. Whereas if WA is another different values, you get your location based attention, additive attention, and content based attention, and similar examples. So again, this is not the complete list. There are a lot more attention alignment scores possible. So now let's just look at an example for image captioning. So previously, what we used to do in like RNN task when we talked about image captioning, we used to take the entire image, and then after the final uh, convolution, then we take these hidden vectors, and then we send it into the hidden states of the RNN. So as you can see, before, what we used to do, we just used to find out what this hidden state would depend upon this particular x0, which is coming from your so h is basically wxh is coming from here, and x0 is your input particular image. This is your start state. X0 is this. So we previously considered only x0 and wxh, but now once we bring in attention mechanism, what we say ki don't just consider the what you said, this particular hidden state, but also consider all the hidden states in between. That is where we consider the blue color addition term, where we say ki now the particular hidden state at some time step depends on all the time steps in that particular sequence from 1 to capital T, or in this case from 0 to capital T. So that is what this particular modification does. So with that, we basically modify and the image captioning task from your previous RNN based image captioning task, and how you want to combine them in the context vector and everything. You can use previous formulas for combining context vectors, and then you can finally get your output, which is be your particular, in this case if your input is this image, your output will be straw hat. So again, like here we said, we don't use FC layer output, final FC layer output entirely, because we lose information which is spatial. Actually, the image should go a little bit up. It's not from here. It should be a little bit up. So I will make this change when you're uploading. So we to see more clearly how it is happening, image captioning with attention. So let's just say this is the final. After CNN, we get the image feature. Sorry, yeah, this is basically the feature map after the final convolution layer. And then we send it to the hidden states, which is just H0, H1, H2. And each of these attention hidden states will output basically two things, A2 and D2, which is one is your distribution over your vocab. Vocabulary in other terms is basically all the possible words in your dictionary. So what I mean by that is before starting any task, you have a dictionary with you saying ki these are all the possible words that you can encounter for this particular task. Obviously, it'll in real life we can't get all the words, but to an extent we get a big dictionary, a huge dictionary, and we find out embeddings of all these dictionaries. Embeddings is nothing but some vector representation of each of these words in the dictionary. And how do you do that embedding? That is beyond the scope of this particular course. You can look into terms like word to vector, or I think there are n-gram models. So you can always Google and see, that is related to how natural language processing happens. But once you create an embedding using any standard embedding technique, so now you get your vectors representation for each word in that particular vocab. So now you basically distribute, you find a distribution across all these vocabularies, across all these words in your dictionary. So each hidden state will basically output these two things. One is the distribution over your vocabulary, and the other is distribution over location. What I mean by distribution over location is in your image, if this is coming from the final spatial map, in this spatial map, what is the distribution like? So if the values are, obviously values will lie between 0 and 1. So the higher the value and closer to 1, it means that particular pixel value is given more priority, and this particular hidden state actually depends on that particular pixel value. So this is what the distribution over L locations. And when I say, if, let's just say if the second, first row, second column element has more priority or more higher value in the distribution for H1, this particular pixel, if you do the, if you backtrack toward the convolution, will actually correspond to some bigger block, bigger chunk in the input image. So in a way, I hope you can able to visualize that each of this hidden state is depending on some patch of this input image, and on some distribution of the output of the words in your particular dictionary. So that is what we want at the end of the day for image captioning. We want to see where to see in a particular image, and once we focus on a particular patch in that input image, what is that particular patch in the input image is translated in terms of words. So that is what this particular task is trying to do. And the input also becomes basically these two features will go as input. One is your words, which is your first word, whichever you give input, and the other is obviously the input will also be your spatial features. So it will take those two as input, and output will be your distributions on that particular image and the vocabulary. So I hope this was clear. Maybe I'll again pause for a quick minute. Any questions, you can unmute and ask. So moving ahead, we'll now talk about the transformer models. So again, these slides are taken from this particular paper, And also, sir explained this. Maybe I'll explain a bit more about these again, each particular step, what is happening. If you want to look at the full recorded lectures are available for each particular explanation of each particular block in detail. I'll again explain a bit briefly about what is happening. So this particular paper, which was proposed in NeurIPS 2017, called "Attention is All You Need," this actually changed the way people started use attention. So previously, like I explained, people used attention in conjunction with some RNN model, like your LSTM or GRU or just RNN. So, and then over a period of time, people realize that you don't need that dependency also. In fact, you can completely eliminate a RNN model and you can just use only attention based models. That's why the name of the paper, "Attention is All You Need." So in this particular paper, they basically come up with four important modules. One is your self attention. Then, based on that self attention, you create your multi attention. And then there is a slight, you can think about this as a pre-processing type of a step called as positional encoding. And then we have your encoder decoder architecture. So in general, if you remember when we were talking about segmentation or anything, encoder decoder, we talked about a concept like that in your segmentation, right? So a similar concept basically exists even for these particular NLP language related tasks also. So what again, the concept remains the same. Encoder takes in the input of your particular, like for example, this particular input in French, and then it tries to create a representation in some subspace which will be the after the end of the final encoder layer, and that will go as an input to the decoder, and then the decoder tries to recreate that particular input, and since we want to do a translation task, it will recreate in another language. That is why the translation task. Whereas in segmentation, if you remember, the recreation was done and you used to form masks over the input image. In this case, you're recreating in another language in itself. So similarity exists between encoder decoder architectures for computer vision and translation tasks. Both of them conceptually are trying to do the same thing, but how they do it is a bit different. For example, in this particular case, like I said, we just take the encoder of the last layer. After the last layer of the encoder, we send that as an input to the decoder. That's what we used to do in UNet architecture, if you remember from the concept when you're talking about image segmentation. Whereas in this case, we say ki instead of that, you take that last layer of the encoder and you send that as an input to all the decoder layers. This is a bit different. So why we do this? We do this so that the attention, when we're doing the decoding part, right? Imagine that the decoding when you're decoding from a lower dimension to higher dimension, there is a lot of noise because you're trying to create something from a lower space to a higher space. So there will be a lot of empty spaces when we're trying to create something from small subspace to a higher subspace. And when we're doing that upsampling also, you'll also encounter a lot of uh, spatial displacement happening. Like in images, when I was talking about the connections in the unit, so a ball and a bat in this image space, if they're close by together, and when we do the encoding part, and when we're upsampling it, there might be a chance that the ball and bat will not be close anymore. They'll be very far because in upsampling we don't have any information from a lower space that where exactly the ball and bat were in actually image. So that's why in UNet we said ki we'll do the skip connections, we'll do the additions at each parallel layer so that the information, the spatial information will be parallelly transferred to that particular decoder layer. Same concept you can imagine that similar type of understanding will be also helpful to understand this particular connecting the last encoder to each and every decoder. We are basically trying to retain that positions where that input could be in that encoded layer, in that encoded output, and we are trying to see that in that encoded output, how is that encoded output related to with the decoder layers. So in brief context, you can always relate it with how the unit architecture is working. So let me go a bit in depth. So first we'll talk a bit about the positional encodings. Yeah, sorry. First we talk about a little bit about the positional encodings. So positional encodings, like I said, it is like a pre-processing step you can imagine. So where you initially want to give some position to that particular word embedding, which will like for example, if the word like the uh, usually they come in the starting, right? So you kind of give them positional encodings as like something which will come in the start. So you create an encoding function like the sign or cause, which inherently what it tries to do is it gives some priority to all the word embeddings you have. So like these usually have starting priorities, whereas some other specific words will not have starting embedding. Positional encoding will don't be higher values. So in that way, you can see that positional encoding helps in basically starting off your encoder values. Like you give some position index kind of a thing when you're encoding. So you can use functions like these, and I think nowadays there are more or less these are the standard positional encoding functions. And people, you can always come up with, you can always look into other encoding functions which are available on, but you can always use these standard ones for your project or any. So after positional encoding, which is like a pre-processing step kind of thing, you can imagine, and now we come into the main crux, which is your self attention. So if you remember, I talked about self attention in this particular. So self attention can be looked at as the scaled dot product attention, which is your self attention. And the formula over here is you have uh, you have two vectors st and hi, and you find the dot product divided by your scaling factor. So if you look over here, you have a similar thing. So in this case, take the scale dot product only, but you obviously have some minor changes to that. So we have three particular elements with us: query, key, and values, which was represent as q, k, and v. And what we do is, if you have your particular input, and if you have your particular input, which is thinking. Now I said every word will have its own embedding. We can use a standard word to vec embedding. You get your vector for thinking, which is x1, and now you will correspondingly have q1, k1, and v1. Where are these q1, k1, v1 coming from? If you look on the left side, each of this capital X is nothing but it's a matrix where each row corresponds to this x1. So you remember that capital X is nothing but a matrix which consists each row as this particular input sequence x1, x2, and x3. So we take this matrix X, we multiply with a weight matrix for called WQ, and the output will be Q1 and then Q2. Similarly, each row will corresponds to that particular input related query. Similarly, if you want key, we do the same thing. We take the input vector input matrix X, and then we multiply it with WK, which is a weight matrix for keys, and then the output will be K1, K2. Each row will corresponds to that particular key of that particular input. And similarly, we do the same thing. Now this WQ, WK, WV is what we learn in during the training. So here these are the trainable parameters. Wherever we say W, right, those are the trainable parameters. So once we get this Q, K, and V, then we do something similar to the at scaled dot product attention, which is Q into K transpose uh, divided by a scaling factor. This is a standard which I think in the paper they use it as 8, multiplied by the V matrix. So here if you look, we used Q into K transpose because uh, ideally what we want is, if you think in terms of each particular element, we want Q1 into K1, which is 112. We divide by 8, which is 14, and then we find out the softmax of that, which is 0.88, and then we multiply with V1. This is what we want. So now if you want to represent each of this element, each of this operation in matrix form, we use this particular Q into K transpose divided by scaling softmax of that into V. So I would definitely suggest and recommend to see how we are going from this particular operation where you are taking each element multiplying and into this matrix format. So this will actually help you understand where to mention the transpose. I think someone was having the doubt in the previous class also, when to mention transpose at for calculating the FCNs and everything. So this is what usually you can always break down these matrix multiplications into similar simple terms, like what is this each row and column multiplication actually doing. So if you break them down, you'll understand that this is what is happening. Each row and each column when multiplied will give this values, and then we're multiplying that with another row of the V matrix. So it's a good exercise. If you break down this matrix multiplication into each row, how it is happening, then you'll understand clearly how we go from this particular left side to the right side matrix multiplication. And once we get that, and once we do this particular operation, this particular operation of softmax, this dot product and multiplication with b, the final result which we get, we call it a Z matrix. And again, the Z matrix, each row will have Z1, Z2, Z3 corresponding to that particular input words in the input sequence. So yeah, this is what self-attention is. So maybe I'll just quickly pause since there's a little bit of mathematics and all. Maybe if you have any questions, you can unmute and ask me. Next, we'll go ahead to how multi-head attention works. Okay. So moving on, then we'll next talk about multi-head attention. So once we get this Z, right, matrix Z, which is this particular thing, we now see how actual multi-head attention works. So these are actual steps 1 to 5. These are the steps. I'll explain in this terms. Like we have first the X matrix, which is your input, where each of this row corresponding to each of the word embeddings, and then we split our particular head. Like we I said, you have three weight matrices, WQ, WK, and WV. This is what we used here. So this particular you can consider as a head. This operations which you talked in this self attention, you can consider it as one head. So we'll have similarly 8 different heads. So each head will output a particular QKV, like you can see Q0, K0, V0, Q1, K1, V1. So we get 8 such heads, 8 such QKV values. All of them are matrices again. And then each of these QKV will undergo operation which is related to this, the scale dot product attention. And then you get 8 such Z matrices, which is Z represented as capital Z0, capital Z1, capital Z7. Make sure you always see the notation difference. When I said capital Z0, it means a matrix and head, basically output of that particular head 0. It's a matrix. Whereas the small Z1 is this particular vector. Similarly for Q, K, and V also. All the small letters with their indexes are always vectors. For matrices, we have capital letters and their particular indices. So then we get this 8 particular Z matrices from those corresponding 8 heads. Then we have this another weight matrix, which is again learnable during training. And we multiply, use this matrix, weight matrix, and we multiply with this 8 heads, and we finally get one capital Z matrix. So this will be our final output of that particular multi-head attention. So this together forms one particular layer, which is called as multi-head attention. Uh, it's not one particular layer. I'll show you more detailedly, but you can just consider this particular operation altogether is called as a multi-head attention operation. It's very simple if you understand what self-attention is. It just replicates that 8 times. And again, this doesn't have to be 8. You can always change, but the problem is more and more if you change, the computational cost will increase. So that is actually one big problem with transformers. Computational cost is a lot, and training takes a lot of time and compute GPU availability. So yeah, this is multi-head attention. Maybe if you have any questions, you can unmute and ask, and I'll just move ahead next to the encoder part. Encoder layers, what they're doing. I'll just quickly pause for a second. If you have any doubts, you can unmute and ask. So then we come to the encoder part. So as you can see, the multi-head attention is actually the main thing which is happening, the main operation you can say for each encoder layer. But apart from multi-head attention, there is some feed forwarding and normalization layers which is needed. So if you can see on the right side, you have your attention mechanisms happening, and then first initially you do your positional encodings. Then after you do your positional encodings, then you do your attention using self attention mechanisms, and then you do some layer normalization and you find your Z matrices, and then you send those Z matrices to a feed forward network to basically find into another subspace, smaller subspace. And then You finally normalize that, and then you do a layer normalization, which is this particular x plus sublayer of x. So this particular type of layer normalization you do. And so in this way, we basically complete one encoder layer, and then you have six such encoder layers in a transformer architecture. So six such blocks corresponds to one encoder architecture of the transformers. Similarly, we have decoder. So here we use mask attention, multi-rate attention, because we use mask because we don't want the corresponding output which has not yet been seen, right? We can't create a dependency on something which we not seen. So that's why it's important to use mask multi-rate attention. Basically, it will mask off all the output elements which are not yet seen. So in a way, you just like ignore them. So that's why it's called as mask multi-attention. And then similarly, you have your other normalization multi-attention steps and your layer normalization step. This entire three operations together is called a decoder layer. We have six such decoder layers, and together they form the entire decoder architecture of transformers. So this is the complete picture. So if you see, your inputs are basically first you send it to the input embeddings, which is then you have your positional encoding, and then you have six such encoder blocks where you each consists of multi-attention and some normalization layers, and then each of this encoder will go as an input to the decoder. Decoder consists of again mask multi-attention, normal multi-attention, and some normalization layers, and finally you have your softmax and then output. So you can see again each of these multi-attention consists of scale dot product. Scale dot product again consists of this particular scale dot product attention consists of these particular operations. This is what we discussed. We started from the right side. We first discussed the scale dot product attention, then multi-attention, and then we went to encoder and decoder. So this is the complete transformers which people mostly nowadays use this type of an architecture. So people applied these architectures not only for tasks like translation and everything. In recent times, people have come up with something called as VIT models and everything, which is for images, where people apply complete transformer based architectures only to do image classification. So they're eliminating CNNs basically. They're trying to attention only uses attention, no RNNs, right? They're trying to use attention only for images also. So they're trying to eliminate CNNs, but yeah, there is research which is still happening in that direction. So I'll quickly pause for a minute or two, and if you have any questions, you can ask. Otherwise, we can move on to the code walkthroughs. Yeah. If you have any questions, you can post it in the chat, or you can unmute and ask. So maybe we can start with the code walkthroughs then. So first I'll explain about the last week lecture, which was the recurrent neural networks. So first we'll explain about a simple RNN based character to character sequencing, how you can do. Then we go a little bit about how you can use the built-in LSTMs, built-in GRUs. And then finally I'll discuss about the Siamese network, how you can create a network like using contrastive learning, how you can train a Siamese network basically. So yeah. Can someone just confirm your Siamese network assignment has been the deadline has is finished, right? I think it was on 20th. Can someone confirm that in the chat? Your week 8 and 9. Sorry, your week 7 and 8 assignment. Okay. Okay. I think there was a Siamese network question in one of the assignments. Okay, maybe. Okay, fine. But I think Okay, let's just go ahead. Maybe I'll explain anyway. So first we'll talk about the RNN based character to character sequencing. So as always, you import your necessary libraries, which is your Torch, and in NN is basically your neural network model in Torch, and then NumPy. And imagine if this is your text, which is hey, how are you? Or these are like different sequences which are available in your data set. And then what we want to do is like if you want to, these are some pre-processing steps you can see. If you want, you can just assign some integer values or some values to these particular characters. How we do that, this is again standard NLP processing, so you don't have to worry about these are like standard in NLP processing, so it's not related to computer vision as such for our particular case. You can look into any type of embeddings. So in this case, basically we assign an integer value to each of the character. This is one such embedding which I was talking about. But in if since it's characters, we can easily give integers. But when there are words and everything, right, you need some vector representation. So I'll just go to the main part of the model, yeah, which is creation of the model and how it will use. So you can look into these starting few steps. It's just understanding how to even convert from each particular sentence. How do you break down into characters, and how you can represent those characters as integers, and also you see how you encode them basically in this particular function. How do you encode one hot encoding of that particular integer? So these are the different post processing and pre processing steps, which is a standard steps. You don't have to worry about those. Which you can always look, and if you have any doubts, you can always ask me in the next session. But I'll come to the main part, which is your model creation. So initially, again, as always, we create our model. We can give any class name. Here we gave it as class model, and you always have to inherit this nn.module library. This basically says that this is a neural network module. So that is very important, like I always said. And like in any class which we create in Python, the first function will be your init function. Init function, like it is usually used to define what layers should be present, or how many number of hidden layers you want, or anything which like a global variables you want to define, right, for your entire class. You usually define in this particular init function. Like in my case, in our case, we first use self.hidden dimensions to understand how many hidden dimensions do we want. Then we say how many number of layers do we want, and this will be the hidden layers. And we define each particular layer, which is your nn.rnn. So, like I said, you don't have to worry about creating each particular RNN operation. Like in RNN or LSTM or GRU, you had like forget gate, input gate, output gate, and the branches were going from one particular hidden state to another state. So all of those in PyTorch, very nicely they have created abstract modules and everything. Good functions they have created. So you don't have to worry about writing those functions from scratch. But what I would suggest you people to do is read the documentation of what this nn.rnn should take as input, like this input size, hidden dimensions, number of layers. These are not just the only arguments which are available. There are a lot more arguments available for each of this module, even for linear layer, RNN layer, convolution layer, any layer, LSTM or anything. Always read the documentation, because then you'll clearly understand. You can go from what you learned in the architecture in the theory part, and instead of directly writing from scratch, you can just understand where and how you want the input to go from theory. Then you can do that particular input connections in this particular arguments. You can give the arguments in such a way that the connections happen. So you can always look into that particular RNN documentation, and you can see what are each of these. So in this case, it's very simple. We just talk about what should be my input size, and then I talk about how many hidden dimensions I want in my particular layer, and how many number of layers I'm having for my RNN neural network. And then after that, I create a simple linear layer also. Again, this takes two inputs, which will be the in hidden dimensions, that how many I want to be, and then finally what should be the output of that particular linear layer, and this usually will be the class size, output size. And then after you create your init function, sorry, after you create your init function, the second important function is your forward function. You always need to have a forward function when you're creating your your neural network, because this particular library, right, this particular class nn.module, which is a PyTorch inherent class, that will always see where this forward function is. And don't rename this also, don't write forward one, forward two. It should be as it is forward, because nn.module, when you do your training, nn.module actually looks where this forward function is defined, and then it will directly take, it'll start executing your module by running line by line in this particular forward function. So if you see over here, you first create you initialize this init hidden is basically initialization of the hidden layer that you can see in the bottom. You first initialize your hidden layer, and then you run the self.rnn, which is your RNN layer. You send the input and the hidden layer which you just initialized, and you get your output and hidden layer. So in this case, since we use a simple RNN, one RNN itself, so you don't have to worry. But when you're creating bigger modules like we did for CNNs, right, you'll have to write where each input is going and where each output is coming. So you can either do that particular, or you can use sequential method, which I explained in the previous live sessions. So you can either create your own each hidden layer, intermediate layers, or you can just create a class called sequential, dictionary called sequential, where you put all the layers and then you can just give the input and get the output. These are the two ways which you can create your neural network in. So similar concept we again use over here also. We create the forward function, we find out what are the output and the hidden values, and then we basically return those output and hidden values. And then once you create your model, you then everything else is again standard how you do for your standard CNN. We create an instance of that particular model, which is called as a small model model, which is the instance of that particular class. And then we send it to GPU. Like I always said, data and model should always be sent to GPU. If one of them is sent and the other one is not sent, then the training won't happen. If both of them are not sent, then training will happen, but it'll take a lot of time because it will happen on CPU. So it's always important that you send your data and your model on the GPU. Then once you do that, you define some hyperparameters like learning rate, how many epochs you want to run, and then obviously you have to define your two important things. What is your loss function? In this case, you can use cross entropy, standard cross entropy, because we just have a vector output will be basically all the characters that are possible, and you basically have a distribution over that characters. So you can just use like a cross entropy loss. And here learning rate can be anything. So we took standard Adam. There are many learning rates available, which you can always look into the PyTorch. So usually people use Adam, but it depends on task to task. Adam is not the only go-to, although most of the problems can be solved with Adam Optimizer. But people always go for others like gradient descent with momentum or other other particular other particular optimizers. And yeah, once you define those, and then you write your simple training loop like always. First, initially we have to make sure that when you in the for loop which you create for the epochs, always make sure that your gradients are zero. This is very important, like I always say, so that any gradients from the previous updated values will not be still lingering out when you want to update your optimizer in this particular time step, so in this particular epoch. So it's always important for you to write this particular line, optimizer dot zero grad, and then you send your model with the input sequence, and then you get your target sequence, and then you find what is the loss. And again, for back propagation to happen, these two steps are very important: loss dot backwards and optimizer dot step. So loss dot backwards is basically it calculates the loss value which is happening, and it will basically tell the PyTorch to be ready to calculate all the back propagated, what is a partial derivatives. And optimizer dot step is basically when you update each of the particular weight matrix with this particular new gradient and like the update rule which you have in gradient descent, right? So that particular gradient update will happen at this optimizer.step line. Before that, your loss.backwards basically calculates exactly the loss and basically tells PyTorch to get ready to backpropagate all the partial derivatives and everything. So yeah, then you do your simple training. You just train for like 100 epochs or something, and you print your loss functions. And then you have a simple predict function. So predict function again, you can look. We are having your one not encoding to be done, because once you get your output, you'll get your output to be a particular number or like a particular integer, right? We have to again decode that into actual character. So that's why we say int to character. When we do char to integer, we are converting from a character, we are going into integer, uh, what is a space. Whereas once the model predicts some integer index as an output, like index 0 or index 1, we have to then use int to character, which basically goes back, takes that number of takes that number which is your 0 or 1 or 2, and then goes back and associates which particular character that is. In this case, since it's character to character sequencing, it is simple. When we go for like I said, higher embedding spaces like word to vec and everything, there's a little bit difference in that. You can always look into the standard processing steps for those. So as you can see, we then see this is some example. We give a word called good, and we are asking totally it should be 15 length, and what will the model predict? So it just predicts this good, I am fine. So it's just a sum sequencing. So it'll actually, good is anyways the input. After that, it'll give a space, then predicts I, then gives space, then predicts A, then M, then each character it predicts basically. And then finally, since we said the output length should be 15, it'll just do for the total 15 characters, including spaces. So this is the total character to yeah, sequence to character, character to character sequencing. So this is one particular RNN task. Nowadays, people, I don't see many people using this particular task, but this is very easy and it's like an intro to how RNNs actually work. So it's very important for you to always start off with this particular task. It will give you a clear idea what is embeddings, how to even create your model, how to even post process once you get your output from the model while you're testing, right? After testing, you get your output, but it'll be numbers. How do you post process that numbers into finally we get the characters as an output? So all of the main ingredients of any sequence modeling task, which usually present in character to character sequencing. So yeah, if you have any questions, maybe you can ask me now. I'll move on to others in a minute. So yeah, this code and all, it's all it's a keeping up. It will be updated in the Google Drive. You can always look into that. I'll share the code, the notebook, collab notebook. Any questions anywhere in architecture or anything? Then we can next go into LSTMs and GRUs. So here again, concept is we don't want to like I want to give you a picture of how the entire script is basically like how do your model input will be, the processing, pre-processing steps, converting into data loaders, how do you create your model class and everything. We don't worry a lot, at least like I said, we don't worry about creating LSTMs from scratch. That you should obviously do, because for a practice, like for people who are studying for the first time these concepts, if you start using these models directly, it'll be hard for you to relate how each operation is working. So as a practice, I think it's also a part of your assignment. It's very important for you to actually from scratch write each operation of each gate, your input gate, output gate, how it is happening. But once you get used to what is happening, the data flow, how it is going on, I think then you can directly use your abstracted modules from PyTorch. You don't have to worry from writing from scratch. Why I would suggest using abstracted models from PyTorch is, firstly, the operations remain the same. What you write from scratch and what PyTorch writes, it's the same. But the only difference is PyTorch GPU version, which we use, they write code very specific to parallel processing, which is using C++ and everything, which is a little bit hard for beginner to start off when they're learning deep learning and writing the models, right? So we write in Python, but they write everything in Python, and they write everything in C++ to make it faster, to use the GPUs and CUDA related programming and everything. So even I'm not very familiar with it, but I think for learning wise, write your scratch code. But when you're actually deploying and everything, don't use the scratch code because it'll take a lot of time. You always use the PyTorch abstracted model. So yeah, that being said, we can again start. So here we use the same first. Always we import important libraries. In this case, all the standard libraries. By now you should be familiar. Your NumPy, Pandas, Matplotlib, and your Torch, and TQDM is something new. So TQDM is like keeping track of a progress of your model. Like for example, sometimes when you see if you have to run a particular okay, maybe I'll give a simple example. When you're copying files in your local system, right? When you move your folders or copy folders or files or delete folders or files, you get uh, a small window pop which says how much time is remaining, how much has been done. Basically, a statistic of what the process, how much process has been completed, and how much process time has happened, and how much process time still is required. So that particular statistic is what TQDM also gives us. So there are more applications of TQDM, but a simple way to understand is it's kind of tells us how much progress has happened, how much of the how much of the data has been seen, or how much of, because even each epoch has a number of steps, right? So how much of that steps has been completed in epoch, and how much of total epochs have been completed. Whatever statistics you want, you can always use TQDM to print that after in your display, so that you'll know how much is done and how much is remaining. And then we use some standard data. So this is available on this particular link. If you print the data, it's a tabular data. Like you can see, you have a date time value, and you have your AEP value. Not very sure what AEP is, but it's a data which I guess you can read up on this content. That doesn't matter. You can just imagine this to be a feature or something, one of the features. So don't worry about what this particular value meaning is. You can read up on the domain of this particular data, but for now, we'll just assume it's one of the features which we have. So yeah, and then you create your particular test and training director. So this particular functions, sorry, this particular code cell, it'll basically take the CSV files and it'll create Panda, and these are the number of features which are present in that particular data frame. So data frame, when I talk about data frame in Pandas, it means basically your particular matrix. You can see like each Excel sheet, if you open it, look like a matrix, right? You have rows and columns. So that particular sheet or that matrix, you can call it as data frame, which is in Pandas. And that particular data frame will have columns which you can index using like this df brackets r, df brackets day of week, then you have df brackets month. So you can just use things like these to, you can use the names to basically index that particular column. And similarly, if you want to index with row, you can use iloc. Basically, if you see in this particular line, you see in this particular line, I use dot iloc. So iloc is usually used to index rows, and if you just mention the brackets and the column name, it will directly index that particular column. So again, you don't have to worry about what this step is. This is like specific to this particular data set. So you, if you, even if you don't understand, you can move ahead. What important thing is, at the end of this particular code file, code cell, what is creating is, we are creating a train x and a train y, and a test x and a test y. So your standard data paths we are creating, your train input features x, your train labels of that corresponding input features, your test input features x, and the test output labels of that corresponding x. So this is what we need. And once we create that, we then convert it into a data set format. So as I said, always it's important to first convert your whatever data you have, be it tabular data, be it images, folders which you give, right? Always convert them into a data set class. So data set itself is an inbuilt PyTorch class, which PyTorch is like a requirement for PyTorch models, because they have their own transformations and everything written in such a way that the input should come from a dataset type of a class. So it's always important to convert whatever input data you have into this dataset class. Sometimes you can easily convert, like for all the previous images cases, it was easy to convert. But if you have tabular data, you can use this tensor dataset. So it converts all the tensors into a dataset format. Like you can see, you give your first you convert the numpy arrays into torch. This is torch dot from numpy, your x and y, and this will become your dataset. So you create data loaders from the dataset. Like I always explain, data loaders are nothing but they take the dataset as an input and they create batches of that particular dataset. And then at each particular epoch when you're training, you upload a particular batch, then you do the update in that particular step, and uh, uh, then you remove that particular batch, and then you upload the second batch and do the second update. So in that way, basically, all those things are taken care of data loader. And there are a few parameters which are important, like batch size. What should be a batch size? Do you want to shuffle your data? Always important to shuffle. Like I always explain, shuffling basically makes your training process smooth and exposed to diverse samples in your dataset. If you don't shuffle, then the training won't happen, because it will only see a particular type of samples, like class for the first few updates, then some second class for the first few updates, and the gradient descent algorithm will never actually converge. Always important to shuffle your dataset. The drop last is a optional thing. You can sometimes keep it as true, sometimes you can keep it as false. Yeah, I think someone has a question. Pavani, yeah, you can unmute and ask.
Yes, yes. Sir, may I know the relation between CUDA, touch, and GPU? Whether if we want to use GPU, CUDA is compulsory or not? I want to know that. In Google Chrome, we can only choose the runtime as GPU. That's it. We are not choosing CUDA and all things. But it was working. In my local system, even I installed CUDA. I'm having also GPU. It is not identified when I'm trying to do the coding in the folder.
Okay, so firstly, CUDA is needed. Like in Collab, you don't have to worry about it because Collab automatically takes care of it. When you're doing in your
Okay.
local system, so just installing CUDA doesn't work. So when your GPU particular, if your particular GPU version and everything comes with only a particular type of CUDA compatibility. So there are
Yes, sir. I follow the compatibility with GPU and CUDA. My GPU also had a 1 GB of storage. And for that GPU, I mean NVIDIA RTX GPU needs CUDA 11.1 drive. So I already installed based on the compatibility I'm getting. But it will not identify the CUDA is available in this model. But I installed.
That's what I'm saying. So installing the drivers is not the only step. I think, did any error or anything come when you're installing the drivers? Because
No, sir. No, nothing.
so
Nothing. Okay. The question is, what is the relation between CUDA and GPU? Whether any one is not sufficient to executing one code, I mean, to executing a contact code.
no, no, all of them should be present. So dependency is basically PyTorch is a language which writes how to make the particular GPU use your model to make it faster training. And how to make the training faster, that language, you can't directly talk to, PyTorch can't talk to GPU. So PyTorch talks to CUDA. CUDA is like the intermediate language. Then CUDA then
Okay.
talks to your GPU. So you need all the three present. PyTorch is needed, GPU is needed, and CUDA in between is needed.
Okay. So in
So
Google column, automatically it will CUDA and all.
exactly, Google Colab already has installed everything and running, so you don't have to worry about all those things.
Okay. Yes. Sir. Okay. So thank
Yeah,
you.
yeah. Any other questions or anything? Okay. So moving ahead. So here we created the train loader, and then here this is a step to actually check if your CUDA is available. So maybe Pavani, did you try these commands? Torch.CUDA is available.
Yes, sir. Yes, sir. First, I will check if those commands in PyTorch. Then it displays talks, but it identifies the GPU. The GPU name it displays, but for code checking, it shows me the false.
Okay. I think somewhere installation in the driver connection must have not happened. Because installing CUDA drivers is a little bit tricky. People usually face problems in that.
Okay.
So maybe
Okay.
just try to uninstall and do it again properly, then that might help.
Okay, so my data set has large database, so every time I have to install and upload it into Google Colab is hectic to me. That's why I install into my local system, but it shows that problem. That's why.
Okay, okay. Just try it out once
Oh,
again. It should be fine. So yeah, and so this particular step is needed, torch.device.cuda. So you send it. So you have to check if your CUDA is activated, basically, in the sense like if GPU is present. If GPU is present, then you send it your particular. Create a variable called device, which is your CUDA device, and you send your model and data, everything into this particular device. Which device, that will be depending on your availability. If it's GPU, this will get activated. Otherwise, the else statement will get activated. So here I created different classes called net, LSTM net. These two particular classes. Again, concept again for these classes remains the same as RNNs, how to create and everything. But the only difference is the layers when we are calling them. So, for example, if in RNN we had the same hidden layers, number of layers, only difference was we called nn.rnn, and similarly here we are calling nn.gru. Similarly for LSTM we'll call nn.lstm. Everything else more or less remains the same. How do you write your forward function? How do you initialize your hidden function? What are the init function variables that should be there? Most of them are same. Only the difference will be the particular module which you want to class, or which you want to call, or which you want to create. So like I said, best practice would be to use to understand the documentation first. What are all the arguments that are happening? So again, here basics things you can see. Mostly you'll be using these only, but for your understanding, if you want to create your own type of LS teams and everything, I would suggest basically going through the documentation and see. But most of the standard ones are something what you see on the screen, right? These are the most standard arguments which we use. If you want to customize more, you can always look into the documentation. So once you create your class, again, follow the same pattern like I just explained for RNN. You inherit your module class. You first create all the global variables in the init class. You create a forward function, and you don't have to create like this initialize hidden like this. This is just for easiness of code we have written. But important two functions that should always be there is init function and forward function. Apart from that, other functions, it's like depending on your particular model, they might be there or might not be there. Important things just should be these two functions, the first two functions, init and forward. Init basically defines the function variables, global variables. Forward basically says, okay, what should the model actually do with the data, its input data it is given. And again, you use a very similar training loop. Here you have your training function, and here in this particular training function, you first, these are some parameters you create. Like if you want to use GRU, call the GRU net class, or if you want to use LSTM, call the LSTM net class. You define your loss functions, your optimizer, and then you start your training loop. In each epoch, you first identify which particular layer are we using, and based on that, you start with your model.zero grad. You send that input to your particular model. So initialize h is basically this h which you're giving, right? So that is coming from the model.initialize hidden. So I forgot to explain this part in the RNN also. So what init hidden is doing is, when you see your RNN architectures, we always say x0, right? Like we say, okay, there's a first token which is given, there's a first h0 which is being given. So that is this particular thing. This h is 0. And once this h0 is, like we say, okay, we start from here and then we take your other inputs, x0, x1, and h1 and h2 comes in. So how do we initialize this hidden? This function you can see over here. So it basically depends on, I think, yeah, we basically use all the zero values only. We try to create all the weights to be zero of that particular hidden layer, and we send it to the device. So once you get your output out basically, and then you calculate loss based on your output, and then you, like I explained, we use dot backwards and dot step to do the back propagation, and then you repeat for each number of like different time steps, sorry, different samples, batches, and then after that for each epoch, and then you finally complete your training. And evaluate is also similar to your standard evaluate. So you can just look into this particular function. This is your training which happens. You can just plot. So this is your data. So energy consumption, everything. So the predicted values are the ones which are in green, and the actual values are the ones which are in blue. So for the first two features, you can see it's getting predicted very well, almost overlapping with the actual. For the last ones, there is some noise in the energy consumption, and also in the last below two ones, little bit of noise over here and here. So yeah, you can see that more or less this is how you create your RNN models using LSTMs and GRUs. So maybe I'll quickly stop for a minute, and if you have any questions, you can unmute and ask. After this, I'll explain a bit about the Siamese network. So if you have no questions, we'll just move to the Siamese network part. So as far as I remember, I think there was a question in one of your assignments. I don't remember, which as was related to the Siamese network. So in general, also we'll talk about how you use contrastive learning, which is a very important concept for in computer vision tasks nowadays. Like contrastive learning, I'll just briefly explain. Basically, I'll show this diagram. Yeah. So in contrast to learning, what we say is we have your input sample, which is this particular circle, and we take a negative dissimilar sample, we have a similar sample. All we want to do is we want to bring the similar sample closer to this input sample, and we want the dissimilar sample to go away. A basic concept like this. And how we do this, all this pulling together and pushing away dissimilar samples, that is all based on this loss function which you see over here. So this first part is what basically finds out how to bring dissimilar things closer. Dissimilar things should be far away, and the other part basically tries to bring the similar things closer. So in this way, we try to basically cluster all the close similar samples together. And once we form such clusters, you can then easily discriminate them. Like all the clusters which are similar, like belongs to cluster one, which is class one. Then you have class two and class three, and so on. So this type of learning is basically called as metric learning, and because we use some kind of similarity metric, contrastive learning is a very popular thing in this. And in that also you have different types, like you have triplet loss, then you have, I think we talked about like 4 or 5 different types of loss functions in, I guess, week 6 or something, then week 6 or week 5. So maybe you can look into that live recording section. In this case, we'll just talk about a simple contrastive loss function, which is this in the equation. But you can replace this loss function with that triplet loss or other types of loss, and you can still proceed with the same manner. So I'll explain about. I won't explain the basics of like the common parts like this plotting functions and everything that you can look into the code. So firstly, yeah. Yeah. So first we import the statements, and again standard step here we use the MNIST dataset. We have MNIST already inbuilt in PyTorch, so we directly load them as train and test dataset. And then we create two functions called as fit function. So when you call model.fit, this particular function will be called. And I'll just briefly tell you what is happening, and I'll come back to you after talking about the model itself. But what this fit function is doing is it'll take your model, which is your Siamese network. It'll take your load data loaders, and then it'll basically do the training also. Like if you look at this, each for epoch loop is run, and each epoch loop you have the train epoch function, which is basically completing all the batches in that particular epoch. So fit function you can see as like a complete training loop, which previously we saw we wrote multiple different functions, right? In this fit function, we combine all of them into this fit function, and fit function calls this train epoch, which will update the model for each batch in that one epoch. and overall for all the epochs we run it for this in this for loop. So this is what these both functions are doing. So this is a standard training loop function which we always use in previous coding examples. But the important part I'll show is where the model creation is done, which is the Siamese network. So so this first we create a Siamese and MNIST data set. So why we create, so once we have the data set, we need to now create pairs for the data set. So this is one different step than standard convolution neural networks, because in standard convolution neural networks you have your input. If it's a classification, you'll have a label like a class name. If it's object detection, you'll have labels like bounding boxes and classes. But in Siamese network, you don't just have your label. Like your label is basically your positive pair and a negative pair. You need to find out pairs which are similar to that particular input pair and pairs which are dissimilar to that particular input pair. We call them positive and negative. So in Siamese network, this is the only different step than other models, is that we need to create a separate function for creating a pseudo data set, you can call, where you create pairs for each particular input sample. You create positive and negative pair. It is relatively easy only. So you just uh, identify the classes and from that particular data set. So you take your trained data set, you identify all the classes, and then for each if you take a class 0, you pick a sample in class 0, and you select one of the other sample in that class 0 and say a positive pair, and you can then pick any other sample from all the remaining 9 classes, because there are only 10 classes in MNIST. In all the remaining 9 classes, you can pick any one sample and say it is a negative pair. And now you get a positive and a negative pair for this particular input sample. That logic itself is basically used, and the entire logic which I said, this is used in this particular line. Sorry, in this particular line. That is the logic. You basically find out your class. First, you divide in class, and then you find out in that class. If I pick a sample from that particular class, we say positive pair. If I pick a sample from all the other 9 classes, we say it as a negative pair. And now I create a dictionary kind of a thing, where each input sample will have a positive sample and a negative sample. So similarly, you do it for your test also, and then you can basically create this entire data set, and you get your samples. Whenever you call this data set, the get item will basically output these things. It will output 2 images and the target, whether it's a positive or a negative. And now we create something called as the Siamese network. Siamese network, as we remember, it consists of something, a backbone architecture, and then the backbone architecture will be usually a CNN or something. And after the final convolution, we convert it into a big vector, and we send it into branches, right? We send the upper branch and lower branch, which will go for the input, uh, one input example and the other input example, x1 and x2, and then we find whether these both are similar or not. So similarly, if you can see the Siamese network, we follow the similar pattern. Assume you have something called as embedding net. I'll explain what embedding net is. So this embedding net will take x1 as an input, given embedding output O1. It'll take x2 as an input and give an output O2, and you have output 1 and output 2. This is your basically Siamese network's output. And where is this embedding 1 coming from? Embedding net. This is where we create over here. This embedding net is nothing but a simple convolution layer followed by a linear layer. So like I explained, you have your convolution layer, backbone layer, and then you convert that after the last convolution, you flatten it and make it into a vector, and then you basically send that output of that linear layer, which is this FC layer, and that will become one embedding. If you send x2 as an input to this embedding net, you'll get another output from the FC, which will be your output 2. So Siamese network is basically, you'll have this output 1 and output 2. And once you get this output 1 and output 2, I'll show you how to calculate the loss. You use these two outputs and calculate the loss based on that equation. And then you finally train your entire Siamese network. So what it is trying to learn is, okay, are these two x1 and x2 similar or not? So in the future, in the testing time, you give two inputs, x1 and x2. All the model should learn is whether these two are same or whether these two are different. If it's correctly saying it's the same or different, then it means that the model has been learned. So what is the loss function? The loss function is written over here. Contrast to loss, it is directly taken from this particular equation. You basically replicate that particular equation over here. So you find out your target, and for the first step, similar step, you just have target. For the dissimilar step, you do one minus of the target, and then you have the margin. So margin is like you can assume that at what threshold value will we consider something is similar or dissimilar. So for example, if I have two vectors x1 and x2, and when I calculate the dot product, right? So when I calculate cosine similarity, it will be somewhere between -1 to 1. So any at what threshold value will I say are they similar? So it should be if the value of the cosine, the dot product or the cosine similarity is greater than 0.5, then it means it is similar. If it is less, it is dissimilar. So that 0.5 is called that threshold. And in cosine similarity, we can say it in that way. In margin, basically, you can assume the threshold like that. At what particular threshold for this loss function will we say that these two input samples are similar or dissimilar? And then we create the loss function also, and then we call the fit function. Basically, we create all these uh, hyperparameters like Siamese, MNIST, and everything. The data sets you create, you send it into data loaders, you create your Siamese network model, and then you call your fit function, and then the final training happens. Yeah, so this is what I wanted to say. So if you can see, after training, the clusters are formed very nicely. Initially, your clusters are like this. Sorry, it's all spread over. Actually, this is also after a particular time step. It's not the original. Original is even more cluttered. This is after a particular time step of training, and this after final, after all the training is done, you'll get something like this. So I went a little bit fast. If you have any questions, you can pause and ask me about how the model is created. I'll always upload this Collab notebook, and you can look into it and get back to me if you have any questions. Maybe if you have any questions right now, you can unmute and ask me. Okay, flattening, what I mean is that, so for example, convolution has three dimensions, right? So convolution will have your height, width, and channels, right? Even after your final convolution, you'll have these three dimensions. So what I mean by flattening is we reduce the three dimensions into one vector representation. So basically, we multiply h, w, and c into, we take those three dimensions and we just multiply them, h into w into c. So now my vector will be h into w into c size. So basically, we take that three-dimensional matrix and uh, combine all of them and write it in one big vector. If you can get it, was it clear, Preeti? So here I used forward function because as I said, this is a module class, right? So that's why. If you don't want to use the forward function, and if you want, you can always create a simple. Like you can write this equation itself. Like once you um, I think it's not over here. So once you get the output, once you send the input to the model, right? You get your outputs one and two. You can write this particular equation itself directly over there. Once you get your output on an output, you don't have to create a class. You can do that also. This we wrote class and everything so that it'll be more like separate modules are there. Loss is a separate module. Network is a separate module and everything. So this is like a more easy way to understand. If you don't want to write it in this way, you can always write it in that. So this is what I wanted to explain in this particular live session. So if you don't have any further questions, we can end the live session here. And thank you all for joining. I'll see you all next week. If you have any questions, I'll stay back for some time. You can always ask me questions. But apart from that, I don't have anything to explain for this class. Thank you.
Can I ask it also?
Yeah, sure. Go ahead.
Sir, in last week assignment, programming assignment, um, in embedding net, sir, I got one error. That is, the input matrix and the output matrix dimensions are not same. Like that, I received an error, sir, in
Okay.
embedding net, in
Okay.
embedding net function. So it is not rectified. So I changed the as a sequential parameters like start equal to add equal to like that. If I write then it will be rectified and it will execute it. I don't know why it takes like this. But in previous, I used to write this non-sequential format which you will shown in today's class. But in last week's assignment, it will show me an error like dimensional matrices are not same. Why it happens?
So when it says matrices are not same, it's usually the layers are getting mismatched. Like for example, three linear layers are there, right? In this, if
Ah,
the
yes.
output of one is not matching with the input of the other, then it
Mhm.
usually happens. Or the output of the convolution network is not like 64 into 4 into 4 after flattening, then this particular error will come. So when it says dimension,
Is it necessary so the dimension is in linear form, 64 and 4 and
I don't know the problem exactly. So it depends on what the input of the problem is, like what there is the input size and how many layers of convolution is there. So depending on how many
okay, the
layers,
image this is 28 into 28, sir.
no,
Layers are in okay,
you,
please.
that's what I'm saying. So we'll have to sit and calculate after each layer what will be the output and how many layers are there and everything. One other simple step will I would say ki just print after convolution network whatever you get, right, like this, right, output over here, this first output, that
Okay.
is the output of
Mm,
convolution. Just print the shape of this, then you'll
okay.
sorry, print the shape of this second output. This is the output of the flatten. So whatever the shape of the
Okay.
second output, that should be the shape over here, that should be the number over here.
Okay. So the sequential layers input and here this output value,
Should
flattened
match.
output value also should match. Okay. And I got mismatch error in this.
Yeah. So
Thank you,
when
sir.
which week was this assignment? I also forgot.
In last week's in week 8 assignment.
Okay, so the deadline is done, right, for that?
Ah, yes, sir. I already completed and it is already evaluated. But
Okay,
my curiosity is why I got the same error. So
sure.
it will be continued. So I lost some marks also. And one more request, sir, related to assignments. So we gave the neat explanation related to programming assignment. It will be very appreciated on our end, and it will be very helpful to us also. But coming to the real, MCQ assignments, you just gave the whether the answer is correct or not. If you provide any explanation related to those part, it will be very helpful to us.
So assignments I don't set usually, so other people set it, well, the written assignments basically. So maybe you can ask them once in the what do you say, discussion forum. Maybe they can help you because I don't set the written assignments. So
Okay, many times I mentioned the same thing in feedback also, sir. In feedback I mentioned the same thing. I'm not getting a proper reply. This is my second time asking this course, so that's why I'm asking. If we got to give the explanation later to sequence, it would be very helpful.
okay,
You are the only person I'm talking with, so that I'm just requesting you that.
sure, sure. Maybe I'll just talk with the other in charge people and maybe they can see about it.
Yeah, yeah, yes, sir. Convey this.
Yeah, sure.
Thank you, sir. Thank
Yeah,
you.
thank you. Okay, then I'll be closing the session. Thank you again for joining.